In this video, we're going to cover the other two types of distance-based clustering methods, which are k-means and PAM. So first, we're going to talk about mean-based clustering, or k-means clustering. And this method attempts to find groups that are most compact in terms of the mean sum of squared deviation, or distance of each observation, from the multivariate center, or centroid, of the assigned group. So the centroid is a value at the center of the cloud. It could be a real observation, or it could not be. Oftentimes it's just, an average value in the center of that data cloud. And then this method uses the distance from this point, the centroid, to all of the observations and wants the smallest distance possible and to create all of all of the observations within the cluster. So to demonstrate this, if you look back at the last video, I showed you a basic visualization of how clustering with distance-based methods works. So remember, we have our multi-dimensions of variables. Here I'm showing you just two, but our observations are plotted in that multi-dimensional variable space. And then the clusters are formed based on the distance of these variables. For hierarchical clustering, all of these observations started separately and then were agglomerated together to finally form 4 clusters. Here you see 3 clusters. But k-means and PAM are both distance-based, and so they're using the same distance method where things have to be close together in space, but they're using partitioning. So you start with all of your observations in a cloud, and then you're dividing up the cloud to minimize space of observations within the cluster and maximize space between clusters. So when it comes to k-means, we have these central points, which I represented with the colored dots within each cluster. And that centroid, then what the method does is it measures the distance in space between that point, that centroid, and all of the observations in your data. And those that are the closest, so these 3 here, would be in the same cluster. And those that are then further away and perhaps closer to a different centroid would be in a different cluster. So this is a visualization of how using that centroid, that kind of artificial point in the center of the cloud, and the distance from that centroid, that's how k-means clustering works. That's why I had those dots in the clusters. All right, so because k-means clustering explicitly computes a mean deviation, k-means clustering relies on the Euclidean distance and thus is only appropriate for numeric data. So technically, we can only use higher order categorical variables if they involve an implicit ordering. So think about education levels. We have primary, secondary, tertiary. Even though those are categorical, those are words, there is an implicit ordering, and that primary is on the bottom, secondary is in the middle, and tertiary is on top. So even though the variables that we're using are 3 out of 4 of them are categorical, there is still a sensible ordering we can use. And so assigning numeric values to those categorical variables and then using them numerically in our k-means clustering method is appropriate. So then what we can do is we run this k-means clustering algorithm just using the command k-means on our numeric columns. So that's columns 2, 7, 8, and 9. We also have to specify that we want 4 centers. So that's 4 centroids. So we're creating 4 clusters. So I can show you that in our data. We have to set our seed. We're going to run that analysis, and we can also then do the segment inspection function on the results. So we get the means and the medians for all 4 groups. I also put those results in R. So what we're seeing here are the means and the medians for all of our 4 groups, so segment inspection function results. And so unlike hierarchical clustering, what we observe is that these groups really appear to vary significantly based on age and less so by marital status. So if you recall, when we looked at hierarchical clustering, we saw that one group was all of the divorced and widowed people, another group was all married people. Here, we're not seeing that same separation that we did. There is some variation. So for example, we see mostly people in group 2 are single. The other groups are more of a mix, some single, some married, some divorced/widowed. But what we're seeing here instead is that there's a lot of differentiation based on age. So it seems like group 1 is everyone in their 50s, group 2 is late 20s, group 3 is for mid 40s, and group 4 is mid to late 30s. We're seeing some separation by age, but just to a lesser degree. The medians are not as different. Also, not a lot of education separation here. Like all the education values, the means are between 1.94 and 2.24, so not a lot of difference there. So it really seems like age is the driving demographic that's creating our 4 clusters using this method. So to dive a little bit deeper into that, I created a box plot of age by segment. So what we're seeing here are the 4 clusters just in the same order as you see in our mean and median graphics from our segment inspection function. And so we're seeing actually that these are perfectly divided. There's almost no overlap between any of these box plots. And what does that mean? It means that the range of ages for group segment 1, cluster 1, is almost entirely distinct from the range for cluster 2 or cluster 3 or cluster 4. So it's very clear that age is the deciding factor when it comes to k-mean segmentation for this data set specifically. And so in general, besides this difference on age, what we do see is that the first group is the oldest, the least educated, and the most likely to be divorced widowed, and most likely to not be in the workforce, probably because they're retired or unemployed. How do we know this? Well, of course, we see that old age. We see that the job number, the average is a little bit higher, so they probably have a little bit higher proportion of people who are white collar, because that was remember 1 was blue collar, 2 is white collar, and 3 is retired or out of the workforce, so probably a higher number of people out of the workforce. We see they're either single, married, because married was 2, or divorced/widowed, because that was represented by the number 3, and they have lower education because that education value is lower than our other 3 groups. So all of that information points to that segment number 1, being a poor target for a potential campaign. And that's because if you think back to the exploratory analysis we did, those types of aspects of our demographics seem to be the least likely to say yes to the offer. But this is just one strategy, one interpretation of the clustering and the results, and there are other options that you should definitely consider, that we're going to consider across our groups and our methods. A key limitation of k-means clustering is that it requires specifying the number of clusters. So remember, I had to set centers to equal 4, and it made me therefore difficult to determine whether one solution is better than another. So if you're going to be using k-means, which actually is one of the most common methods of clustering out there, you want to be sure that you repeat the clustering analysis for a variety of values of k, and then determine which group of clusters and which segments are the most informative for your business goals. So I would maybe try this for 2, 3, 4, and 5 clusters if this was the only method I was going to use it for a specific question, to make sure that the number of clusters I'm looking at and the results and conclusions I'm drawing from them really do make the most sense for the goals of the business. One other thing I want to point out is that these group labels are arbitrary. So remember, so here we're seeing that group 1 is the oldest. That may or may not have been the case for hierarchical clustering, and for the other analyses we're going to do. The group numbers are just arbitrary. So the categorizations and general descriptives of group 1 for one analysis is going to be really different than group 1 for another analysis. So it's okay that the numbers change. I wish that they were consistent to make things a little bit easier, but they're just not. It's just the way it is. So the other third and final distance-based clustering method I want to cover is called partitioning around medoids, so PAM. So partitioning around medoids is based on the search for k representative objects, or medoids, among the observations of the data, meaning that we're using actual observations as the center point. So that's how it one of the key ways that it varies from k-means is that instead of using a kind of average perhaps artificial center point around which to create those distances to create the clusters like we did for k-means. PAM uses a medoid, which is an actual data point in the center of the cluster. So after finding a set of k medoids, k clusters, so here k just means the number of clusters you're setting. So that number of clusters are constructed by assigning each observation to the nearest medoid. The goal is to find k representative objects that minimize the sum of the dissimilarities of the observations to their closest representative object. So the PAM function is more robust than means-based clustering because it minimizes the sum of dissimilarities instead of using the sum of squared Euclidean distances. You don't have to worry about that level of detail. What you do need to know is that PAM and k-means differ in that k-means you can only use numeric variables. Remember, we had to use the numeric versions of our categorical variables, but PAM, you can actually use categorical and numeric variables, and it actually uses the dissimilarity matrix, that DAISY function that we use for hierarchical clustering. So that's the second key way that it differs. So I have a summary of these differences here. PAM uses a central point, that medoid, that's a real observation in your data, whereas k-means makes up a central point, that's centroid, that is in the center of your data, around which center of your cluster, around which the cluster is formed based on distances from that point. And then the other key difference is that PAM is you can use mixed data types, so categorical and numeric, and it can use that dissimilarity matrix like we used in hierarchical clustering, but k-means you have to use the numeric data only. So I'll show you real quickly what we get in our part PAM. So we have to set a seed. This here's the function, that second line. Then we do our segment inspection function. Took a sec, but here are the results. I put them in our notes as well. So these results reveal yet a different clustering solution for our segmentation data relative to both hierarchical clustering and k-means clustering proposals. So you see we have 4 groups. We specified 4 groups, but they differ in different ways. So the groups generated by PAM clearly differ on all 4 of these variables. So for example, we see that this 4th group is young, single segment. So their marital status is, the average is quite low, 1.2. The mean is 1. The median is 1. So that indicates that most of them are single. They're also quite young. They're the youngest age group with the mean and median at 32. Then the 4th group, the first group is the oldest and the least educated. So that's kind of what we saw for k-means as well. They include slightly younger people. So for the oldest age group, or the oldest segment in k-means, the average age was around 55. Here we're seeing the oldest group is, the average age is around 48, median's 49. They're also the least educated. So here education seems to vary more across groups than for k-means. So here we're seeing that group 1, low education level, has high for group 1, and then high education level for group 2. Right, so the second group is white collar, highly educated. So these facts point to this proposal that the second group is the superior group to target for a campaign, and the first group might be a bad target for our campaign. So a useful tool for determining the number of clusters is something called the silhouette function, which is unique to PAM. And the silhouette coefficient is a measure of how similar an object is to its own cluster, aka cohesion, compared to other clusters, aka separation. This value ranges from -1 to 1, and a high value indicates the object is well matched to its own cluster and poorly matched to neighboring clusters. So if most clusters have a high silhouette coefficient value, then the cluster configuration is appropriate. If many observations have a low or negative silhouette value, then the clustering solution may not be appropriate. So we're going to get into more details about how to use the silhouette coefficient, but I just want to, for now, for you to understand that this value is derived from PAM, and it helps evaluate if the number of clusters that you're using is appropriate, or if perhaps you should try a different number. So I'm going to show you the cluster plots for both k-means and PAM. So remember, the cluster plot is that visualization Here we see it for hierarchical from the last video. It's that visualization of how much these clusters are similar versus different. It's represented by how separate or overlapping these ovals are. So if we look at the cluster plot for k-means, we see that there's some overlap, definitely, especially it seems like cluster 4 is kind of overlapped by a lot of the clusters, but there's also some separation. So seems to be doing a decent job of creating distinct clusters. Could do better, but could definitely do worse. And we can also look at the same cluster plot for PAM. And here I think there's maybe a little bit more separation than for k-means, because you can see a lot of space that's not overlapping at all for 3 of the segments, whereas for k-means it seemed like only one segment was really, kind of on its own. But yeah, just a visualization to see if you're using the right number of clusters, if they're distinct, or if they're completely overlapping or not. So that concludes the final 2 types of distance-based clustering methods.